Today we are going to discuss set operations. Um, Two or more sets can be combined in different ways. For example, let's start with the set of mathematics majors at your school and a set of computer science major at your school. We can form a set of students who are mathematics majors or students who are major in computer science. Another, okay, another group that we can create would be the set of students who are joint majors in mathematics and computer science. And another would be the set of all students not majoring in mathematics or in computer science, and so on. Okay, so that would be somewhat introduction of what we call set operations. Okay, let's start with, let's have this definition. Let A and B be sets. The union of the set A and B, denoted by A, U, V, U, B rather, is the set that contains those elements that are either in A or in B or both. So, in other words, when we are talking about when we are talking about the union of sets A and B, okay, an element, okay, an element X belongs to the union of the sets A and B if and only if X belongs to A or X belongs to B. So in other words, when we are talking about the set, the union of two sets, let's say set A and B, so the union of A and B would be the set of X such that X is element of A or the X is an element of B. Okay, so the Venn diagram below shows the how the union uh, is being illustrated. Okay, so you have their set A and B, and then the area that represents the union of A and B is the shaded area within either the circle representing A or the circle representing B. Okay, for example, let's say you have two sets, uh, a set containing elements of 1, 3, 5, and another set containing elements of 1, 3, 2. So the union of the sets 1, 3, 5, and another set containing 1, 3, 2 would be a set containing the elements of 1, 2, 3, and 5. Okay. Another concept that we need to be clarified would be let A and B be sets. The intersections or the intersection of the sets A and B, denoted by A or B, is the set containing those elements in both A and B. So in other words, an element X belongs to the intersection of the sets A and B if and only if it belongs to if and only if the X belongs to A and X belongs to B. So in other words, when we are going to have the intersection, you could have the set A intersect with set B is a set containing X such that X is an element of A and the X is an element of B. So to illustrate in the Venn diagram, the shaded portion in this illustration would be the representation of the intersection between A and B, okay, in the Venn diagram. Okay, so for example, let's say you have a set containing element of 1, 3, 5, and another set containing 1, 2, 3. The intersection between the two sets would be 1, 3. Okay, so we have this concept. Two sets are called disjoint if their intersection is the empty set. Okay, for example, let's say set A containing elements of 1, 3, 5, 7, 9, and set B containing elements of 2, 4, 6, 8, 10. So if we are going to have the intersection between the set A and B, okay, take note that our set A would be 1, 3, 5, 7, 9, and our set B would be uh, elements of 2, 4, 6, 8, 10. So if we are going to get the intersection between the set A and B, the answer would be empty set. So in other words, there's no common between the set A and B. In If there would be no common between the two sets, then that would be uh, disjoint. Okay, they don't have any common elements except for empty set. Okay, so another, um, we are often interested in finding the cardinality of the union of two finite sets, let's say A and B. Okay. Note that the absolute value of A plus the absolute value of B counts each element that is A but not in B, or B but not in A exactly once. And each element that is in both A and B exactly twice. Thus, if the number of elements that are in both A and B is subtracted by from A plus B, okay, absolute value of A plus the absolute value of B, the elements in A intersect B will be counted only once. Okay. So the generalization of this result of unions of the arbitrary number of sets is called the principle of inclusion exclusion. The principle of inclusion exclusion is an important technique used in the enumeration. Okay. So let's have another concept to be discussed. Let A and B be sets. The difference of A and B, denoted by A minus B, is the set containing those elements that are in A but not in B. So the difference of A and B is called complement of B with respect to A. Okay. The difference of A and B is sometimes denoted by A backslash B. So the element X belongs to the difference of A and B if and only if the element X, which is an element of A, and the X is not element of B. Okay, this tells us that when we are going to have the difference of two sets, let's say set A minus set B, this is actually a set containing X such that the X is an element of A, but uh, and rather, and the X is not element of B. So this would be the illustration of A minus B. Okay, so um, let's have an example. Okay, so if the element, if we have two elements, let's say 1, 3, 5, and uh, another element containing the another set containing the elements of 1, 2, 3, okay, then if we are going to get the difference between the set containing 1, 3, 5 and the set containing 1, 2, 5, 1, 2, 3 rather, then the answer would be an element a set rather, a set containing an element of 5. Okay. So another, you have there, let U be a universal set. The complement of the set A, denoted by A bar, okay, is a complement of A with respect to U. Therefore, the complement of set A is the union, the universal set rather, minus A. So the area shaded in the illustration, okay, here is actually the representation of complement of the A, complement of A with respect to the universal set. Okay. So, for example, let's say that you have a set containing the vowel of the English alphabet, then the complement of set A would be all the letters that is not vowel, which is the consonant. Okay. So that's an example. So let's have set identities. So this table lists the most important set of identities. Okay. So for example, you have here that the union of the intersection, rather, the intersection of A and universal set would be A. And then the the union of let me repeat. The intersection between A and the universal set is the set A. And the union of set A, okay, and empty set would be set A. That's identity loss. The domination loss would be when you have the set A union with set U, or the universal set, that's equal to the universal set. And if you have a set A intersect with the null set, that's equal to the null set. You also have the idempotent laws, the intersection, the union rather, the union or the intersection of A and A would be A. Then we also have the complementation law. The complement of the complement of A would be the A. And then commutative law, okay, commutative laws rather. So you have the A union B would be B union A. And the A intersect B would be B intersect A. Associative laws, you have A union to the quantity B union C would be equal to the quantity A union B union C. Okay. And then A intersect with the quantity B intersect to C. That would be the same as the quantity A intersect with B and then intersect with C. Distributive law, you have A union to the quantity B intersect C would be the union of the two sets A, B, which intersects to the union of A and C. Okay. Or A intersect to the quantity B union C. That would be the same as the intersection of A and B which union to the intersection of A and C. We also have the De Morgan's law. You have the complement of A union B would be equal to the complement of A union to complement B. Or we could also have another De Morgan's law. The complement of A union B is the same to the complement of A intersect complement of B. And then we have also the absorption laws. So you have A union with A uh, intersect B would be equal to A, and A intersect to the quantity A union B is equal to A. And then we have the complement laws. You have the A union to the absolute, not the absolute, the um, complement of A would be the universal set. Or you have if A intersect to the um, what do you call this one? Complement of A would be uh, null. So let's have an example. Use use the set builder notation and logical equivalence to establish the first De Morgan law, which is the complement of A union B, A intersect B would be equal to the what do you call this one? The complement of A union to the complement of B. Okay. So for our solution, okay, the complement of A intersect B, okay, uh, is actually a set of X such that the X is not element of A union B. So this is actually by the definition of the complement. Now, if that would be the case, then you could have that the set uh, which contains X such that it is uh, not not an element. It is not that the X is an element of A intersect to B. Okay, that is the definition of does not belong symbol. Okay, we all know that. Now, if that would be the case, then we could also have that a set of X such that it is not um, the X is not an element of A and the X is not an element of B. Okay, so that is the definition of intersection. Okay, so if that would be the definition of intersection, then you could also have that the X, a set of X such that it is not uh, the X is an element of A or it is not that the X is an element of B. Okay. So this is actually the first De Morgan's law of logical equivalence, if you can still remember with the previous discussion that we had. If that would be the case, then we could also have that uh, a set of X such that the X is not an element of A, it's not an element of A, or the X is not an element of B. This is actually the definition of does not belong. Okay, does not belong symbol. Okay, if that would be the case because they do not belong to each other, then we could say that this is also a set, okay, containing X such that the X is an element of the complement of A, or the X is an element, okay, of the complement of B. So this is the definition of complement. If that would be the case, then we could have this is can be written as a set of X such that the X is an element of uh, the complement of A union to the complement of B. This is the definition of union. If that would be the case, then this, okay, set builder notation can be written as the complement of A union to the complement of B. So note that besides the definition of complements, unions, set membership, and set builder notations, This proof uses a second De Morgan law for logical equivalence. So proving a set identity involving more than two sets by showing each side of the identity is a subset of another or the other often requires that we keep track of the different cases. Okay. Okay, let's try to continue. So let's have generalized union and intersections. Okay, so because the unions and intersections of sets satisfy associative laws, and the set A union to B union to C and A intersect to B intersect to C are well defined. That is, the meaning of this notation is ambiguous when A, B, and C are sets. That is, we do not have to use the parentheses to indicate which operation comes first because A union to the quantity B union C is just equal to the quantity A union B union C. And the A intersect to the quantity B union C, intersect C rather, is just the same with the quantity A intersect B intersect C. Okay. Note that the A union to B union to C contains those elements that are in at least one of the elements A, B, and C. And that A intersect to B intersect to C contains those elements that are in all of A, B, and C. So these combinations of the three sets A, B, and C would be are actually illustrated in this Venn diagram. So you have there in the first Venn diagram, you have the A union to B union to C, which is the shaded portion, and the A intersect to B intersect to C is actually represented by the shaded portion of the Venn diagram. Okay, so let's an example, let set A contains 0, 2, 4, 6, 8, set B contains 0, 1, 2, 3, 4, and set C contains 0, 3, 6, 9. What are the A union to B union to C and A intersect B intersect C? So for our solution for the first problem, so here, um, the A union to B, union to C contains those elements in at least one of A, B, and C. Hence, we could have a set containing 0, 1, 2, 3, 4, 6, 8, and 9. So that's the answer for the first problem. Now, uh, the set A intersect to B intersect to C contains those elements in all three of the set A, B, and C. In other words, when you have A intersect to B intersect to C, that would be okay, the element that is or that are common to the set A, B, and C. So in this case, only the element 0 is the common element to the set A, B, and C. Okay. So let's have another concept. The union of the collection of sets is the set that contains those elements that are members of at least one set of collection. So by notation, we could have, okay, in that case, you could have the set A sub 1 union to set A sub 2 union to so on to the union of A sub n, which can be written as the union of the the set A sub I from 1 to n. Okay, to denote that the union of the sets A sub 1, A sub 2, up to A sub n. Okay, so another concept, the intersection of the collection of sets is the set that contains those elements that are members of all the sets in the collection. So in other words, when we are going to have A sub 1 intersect to A sub 2 intersect to A sub up to A sub n, that would be okay in illustration you could have A sub 1 intersect to A sub 2 intersect to so on up to A sub n, which can be written as the intersection of A sub I from 1 to n. Okay, to denote the intersection of the sets A sub 1, A sub 2 up to A sub n. Okay, so let's have functions. So for the functions, uh, it's already discussed to you when you were in your high school, but let's have the functions. In many instances, we assign to each element of the sets of a set a particular element of the second set, which may be in the same at the first. For example, suppose that each student in the discrete mathematics class is assigned to the letter grade from the set A, B, C, D, and F. Okay, A, B, C, D, F rather. And suppose that the grades are A for Adam, let's say C for Cho, B for good friend, and A for Rodriguez, and F for Stevens. So the assignment of the grades is actually uh, so let's have these important notes, important definition. Let A and B be non-empty sets. A function f, okay, from A to B is an assignment of exactly one element of B to each element of A. So we write the f of A equals B. E of B is the unique element of the set B assigned by the function f to the element A of the set A. If the function f is a function from A to B, we write that you have the function, okay, A maps B. So the functions are sometimes also called mappings or transformation. Okay, so functions uh, are clearly specified in different ways. Sometimes we explicitly state the assignment. Okay, oftentimes we give formulas such as f of x is equal to, let's say, x plus 1 to define the function. Okay, other times we use a computer program to specify a function. So the function f, okay, where a maps to b, can be also be defined in terms of the relation from a to b. Recall from the previous discussion that you had that the relation from a to b is just a subset of a by b. So the relation from a to b that contains one and only one ordered pair AB for A, uh, every element A in the set A, okay, and defines the function f from A to B. So this function is defined by the assignment of f of A equals B, where the ordered pair AB is the unique ordered pair in the relation and has A as its first element. Another concept is if the f is a function from A to B, we say that A is the domain of the function f and set B is the codomain of the function f. So if f of A is equal to B, we say that B is the image of A and A is a pre-image of B. The range or the image of the function f is the set of all images of elements of A. Also, if the function f is a function from A to B, we say we say that f maps A to B. So when when we define a function, we specify its domain, its codomain, and the mapping of the elements of the domain to elements of the codomain. So two functions are equal when they have the same domain. They and have the same codomain. The map of each element of their common domain to the same elements in their common domains. So uh, if we change either the domain or the codomain of the function, we then obtain a different function. If we change the mapping of the elements, then we also obtain a different function. So you have there the illustration. Okay, so you have there an example. What are the domain, codomain, and the range of the function that assigns grades to the student described below? So you have there Adam, True, good friend, Rodriguez, Stevens. So for our solution, let G be the function that assigns a grade to a student in our discrete mathematics class. So note that the function G, which is contains Adam, would be equal to 8, okay, for instance. So in this case, the domain of G, okay, the domain of G, okay, is the set of Adam, Chu, good friend, Rodriguez, and Stevens. So this is the domain of the G. And of course, the codomain, okay, the codomain of G would be A, B, C, F. We do not include the D because D has no element that corresponds to the uh, the domain. Okay. Another concept that needs to be clarified. Let f sub 1 and f sub 2 be functions from a to the real number. Then the sum of the two functions, okay, are also functions from a to the real number defined for all x elements of a. So you have there uh, the sum of, okay, you have the quantity f sub 1 plus f sub 2 of x is equal to the f sub 1 of x plus f sub 2 of x. And then you also have f sub 1 times f sub 2 of x is just equal to the f sub 1 of x multiplied to the f sub 2 of x. Okay. Another is let f be a function from a to b and let s be a subset of a. The image of s under the function f is the subset of b that contains the images of the elements of S. We denote that we denote the image rather of S by the f of S. So the f of S is a set of T such that there exists S that is element of the set S that T is equal to f of S. We also use the shorthand f of S, elements of S, uh, no, 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 no. F of S such that S is an element of the set S to denote this set. Okay. So let's have an example. Let f sub 1 and f sub 2 be functions from R to R such that the f sub 1x is equal to x squared and the f sub 2 of x is equal to x minus x squared. What are the functions plus f sub 1 plus f sub 2 and f sub 2 times f sub 1 times f sub 2? Okay. For the first one, you have the f sub 1 plus the f sub 2 dx is just equal to the f sub 1 of x plus the f sub 2 of x, which is this one is equal to x squared plus x minus x squared, which is equal to 2x squared plus x. No, 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 no. Wrong. I am wrong. Because this is addition, okay, because this is addition, then you could have this one is cancelled out. What remains is x. Okay. Another f sub 1 of f sub 1 times f sub 2 of x is equal to x squared um, times x minus x squared, which is equal to x cubed minus x to the fourth. Okay, so let's have one-to-one and onto functions. Okay, so when we are talking about one-to-one and onto functions, okay, note that the function f is one-to-one if and only if the f of a is not equal to f of b, whenever a is not equal to b. This way of expressing that f is a one-to-one is obtained by taking the contrapositive of the implication in the definition. So we can express that the function f is a one-to-one using quantifiers such as, okay, for the quantifiers, we could have um, for all a, for all b of the f of a would equal to f of b implies that a is equal to b. Or the equivalent of that would be for all a, for all b, okay, you have a not equal to b implies that the function of a is not equal to the function of b. Okay, where the universe of disclosure is the domain of the function. Okay, so let's have this one. Determine whether the function f from elements a, b, c, d to 1, 2, 3, 4, 5 with f sub a equals 4, f sub b, f of b rather is equal to 5, f of c is equal to 1, and f of d is equal to 3 is 1 to 1. Okay, in this case, remember that you have a f of a is equal to 4. So if you have a corresponds to 4, and then if you have b, it corresponds to the number 5. C corresponds to 1, and uh, D corresponds to 3. So clearly, this is a 1 to 1. Okay. Determine whether the function f of x is equal to x squared from the set of integers to the set integers is a one-to-one. So in this case, we could really say that this is not a one-to-one. Why? Because the f of x, which is equal to x squared could have the value of f of 1, which is equal to the value of the f of negative 1, which is equal to 1. So in other words, you have two elements in the domain that has a common element in the codomain. Okay, so in other words, this is not one-to-one. Okay, we have this concept. The function f whose domain and codomain are subsets of the set of real numbers is called increasing if the function of x is less than or equal to the function of y, and strictly increasing if the function of x less than function of y whenever x is less than y and x and y are the domain of the function f. Similarly, the function f is called decreasing if the f of x is greater than or equal to the f of y, and strictly decreasing if f of x is greater than f of y whenever x is less than y and x and y are the domain of the function f. So the word strictly in this definition indicates strict inequality. So the function f is increasing if there exists x and y, there exists x and there exists y, wherein x is less than y implies that the f of x is less than or equal to the f of y. So strictly increasing if um, you have for all x and for all y, there exists x less than y implies that the f of x is less than f of y. So it is decreasing if you have for all x, for all y, okay, you have x less than y, implies the f of x is greater than or equal to the f of y. So uh, that the universe of the closure of the domain is the function. Okay, so a function f and from A to B is called onto or surjection if and only if for every element of B, okay, for every element of B in the set B, there is an element of A, uh, element of set A with the f of a is equal to b. So a function f is called surjective if it is onto. Okay, so you have there an example of onto function or onto relationship. So the function f is onto if there exists y, uh, there exists y in the x of f of x equals y, where the domain for all for x is the domain of the function, and the domain of y is the domain of the function. Okay, so let's have an example. Let the function f be the function from the elements a, b, c, d to 1, 2, 3. Define a, f of a is equal to is equal to 3, f of b is equal to 2, f of c is equal to 1, and f of d is equal to 3. Is f and onto function. So in this case, because all three elements of the codomain are image of the elements in the domain, we can see that the f is on 2. So that's it. Uh, is the function f of x is equal to x squared from the set of integers is a set of integers on 2. So for the solution of this one, the function f is not on 2 because there is no integers. Okay, there would be no integer x with x squared equals negative 1. That's for instance. So that by that example alone, that could stand that the function f of x is equal to x squared is not on 2. Okay. So this would be the illustrations of different types of correspondence. So the letter A, this is one-to-one but not onto. Okay, here. This is one-to-one but not onto because there's an element in our code domain that has no corresponding element to the uh, domain. This is onto but not one-to-one because there is an element in our code domain that has two corresponding elements in our domain. This is an example of one-to-one and onto because each element in our domain has a corresponding elements in our code domain, and there's no such element in our code domain that has another element in our domain. So this is one-to-one and onto. Neither one-to-one or onto because uh, you have an element in our code domain that has two elements, corresponding elements in our domain. And there is also an element in the code domain that has no corresponding element to the domain. Another here, this is not a function because there exists an element in the domain that has two corresponding elements in the code domain. Okay, so the function f is one-to-one correspondence or bijection if uh, it is both one-to-one and onto. Okay, so we also say that the function that such a function is bijective. Okay, so, so let's have this one. Let f be the function from the set A, B, C, and D to the set 1, 2, 3, 4. With the f of A is equal to 4, f of B is equal to 2, f of C is equal to 1, and f of D is equal to 3. If the function f is the function f a bijection. Okay, so in this case, okay, the function f is one-to-one and onto. Okay, it is one-to-one because no two values in the domain are assigned to the same function value. It is onto because all the four elements of the code domain are images of the elements in that domain. Hence, the function f is a bijection.